Swayam Prabha. Digital India. Educated India.
Welcome back to this course on foundations of cyber physical systems. So, in the last lecture we started with this proof on whether this non EDD schedules are optimal or EDD schedules are better. So, let's move ahead from that point. So, I think we had been discussing this. So, we had this two options of a two task system. We have an EDD schedule and we have this non EDD schedule here, right. So, if you look at the non EDD schedule, we have a task which has this deadline. In this case, you have this task which has a deadline that is later on, right. This task I which has a deadline later on, it is executing first, but in this case a task which has a deadline which is earlier is executing first, right. So, this is the basic difference between these two tasks here. So, in one case we saw that well this is our max lateness equation. In the other case we have this the max lateness is given by these two differences, right. It is either this or this, and we made one observation that well f I prime is nothing but this is equal to f j, right, because that is the point when both tasks finish. So, f j must be equal to f I prime, right. So, please ignore this part here, and we will see that well what really is the case. Can I show that in both the EDD schedule will give me a max lateness value that is smaller than the non EDD schedule. If we can prove that, we are done. We have shown that well at least in the two task system whatever is the EDD schedule that is actually minimizing the max lateness. So, let us move ahead. So, what we really have here is this situation, right. I mean f I prime minus d I and f j prime minus d j. So, let us see let us do a case analysis that suppose this is the resulting max or this is the resulting max. I mean in both cases what really happens, is this situation better than this situation with respect to the lateness. That is how we will do a case analysis. And why we have to do the case analysis, let us understand. I will just repeat this, that these two intervals, it is not that they are contained inside each other, something like that, right. So, this is all symbolic. So, we need to see in both cases what is happening. So, let us go forward and analyze this both of these situations. So, there would be a case on where we will be considering that well this f I prime minus d I is the maximum, right. So, let us see that situation, that f I prime minus d I let us say that's the bigger one, right. Now, observe one thing, like we said earlier, that f I prime is f j, right. So, and of course, we know that d j here is smaller than d I, that has been our initial task setting, right. So, if we have f I prime equal to f j and d j is less than d I, we have f I prime minus d I to be less than equal to f j. I mean that is basically the same value, but earlier we are subtracting d I and now we are subtracting a smaller value. Okay. So, if I just subtract a smaller value here, right, then this is bigger, right. So, I have f j minus d j to be larger than f I prime minus d I. So, I will just repeat. What we are doing is this is the max lateness f I prime minus d I, right. Now, what we are saying is let us remove f I prime with f j, right, and let us see what happens. I mean now instead of subtracting d I, if I subtract dj, right. So, if instead of subtracting di, so essentially if I look at this figure, so again this is same as fj, right, they are both same. Instead of subtracting this, if I subtract this, right. So, I have a smaller magnitude, but right. So, this is a smaller magnitude. So, if this is fj minus dj, right, and this is a smaller magnitude, but it is in negative. So, what I will have is a negative smaller magnitude is going to be larger than this one, right. So, in that way, in this case I have this and if you observe what is fj minus dj, if you just turn over to my previous slide, that exactly is L max. That means, for the EDD schedule, the non-EDD schedule, what is maximum lateness, right. So, I can write this L prime max is less equals L max. So, in case in this maximum lateness, the first argument is really the max, which is case 1. We have shown the maximum lateness here is smaller for the EDD. Now, take the other argument which is fj prime minus dj, right. So, if you take that one, then this is your maximum lateness L prime max, right. Now, we know for one thing that well fj prime is less equals fj, right, because fj prime is here and fj is here, right. So, I can always write just replace fj prime with fj, right. So, then if I consider this interval fj minus dj, right. So, this again is the smaller interval, smaller in magnitude. That means, I can just say that well fj minus dj is greater than this L max prime, because it is negative with a larger value. With respect to that, something negative with a smaller value will be larger than this, right. So, and this is again L max, right. So, in this case again I can argue that L max prime is less than equal to L max. So, in effect, using both the cases, what we are able to show is that this L max prime, which is the maximum lateness, is smaller than the L max, which is the maximum lateness for non-EDD, right. So, this is it, right. So, when I am following EDD, I am minimizing the maximum lateness for the two task system. In general, it is a difficult proof, but we can definitely show that for any number of tasks this argument will hold, right. So, this is the statement that we can make, that schedule 2 has maximum lateness which is no greater than that of schedule 1. So, that has been our entire hypothesis. So, we can say that EDD schedule, that is the schedule 2, it has minimum value of maximum lateness of all schedules, because in a two task system you just have two possibilities. So, this is a simple proof, but as you can see that there are some cases and arguments to be made here, but we are able to show that why EDD works. And in general, when you want to put EDD in practice, you need to support arrival of tasks, right, because the idea of EDD is that well you are given a static task set. So, if you extend this with arrival of tasks, then we have this algorithm of earliest deadline first execution, the EDF algorithm. So, EDF is an algorithm or Horn's algorithm. It supports arrival of tasks and better to say periodic arrival of tasks. Okay. So, if I am given a finite set of non-repeating tasks with associated deadlines and an arbitrary arrival times. So, observe this, the arrival time here would mean the initial offsets of the tasks. Okay. An arbitrary and any algorithm that at any instant executes the task with earliest deadline among all the arrived tasks is optimal with respect to minimizing the maximum lateness. So, this is what we have shown for the small example, and we are saying that well this is true in general. You are given this task set and you are told that well for this task set you have these are the current deadlines, right, and the tasks can arrive at any point. Okay. And among all the different scheduling algorithms which you can use to order the execution of the tasks, that algorithm which uses the notion of earliest deadline for deriving the ordering of the tasks is the one which is optimal in minimizing the maximum lateness. So, that is what we are arguing. Now, if we can apply this hypothesis time and again. So, suppose now one new task instance arrives, right. So, your set of arrived tasks has changed, right. So, for this set of tasks you calculate that what are the deadlines, okay, and the one which has the earliest deadline you start executing it. Okay. So, that is how EDF will work. You have a set of task instances that are there in your queue. For them you have checked that which one has the earliest impending deadline, right, and you execute that. And in while doing this, well, another task may be added to the system, and if that task has even earliest deadline, you will re-evaluate. That is why EDF is also preemptive, right. So, suppose while executing some task which was earlier having the earliest deadline, a new task has arrived, your arrived set has changed, right. So, look at this argument here, we are not talking about repetition, we are looking at it for a single instance. We are saying that at this instance you have a set of non-repeating tasks and associated deadlines and arrival times, and you are saying that well among them whichever one has the earliest deadline you execute it. Now, extend this argument to the periodic case. So, a new task will arrive. Whenever the new task arrives, it is almost just look at it again that you have this same non-repeating task set, but it has extended with this new instance of arrival of some task. Okay. And then again you apply the algorithm. That means, you see that among these pending task instances of different task types, which one has the earliest deadline. If this one is something that is pending with respect to something that was executing, you preempt it and again execute. So, that is how EDF will really work, and it can be shown that among all such algorithms which are now. So, now what is happening? Whichever task has priority to be high or low, that is changing based on the instance of the task. Some instances may have lower priority, but depending on arrival times, depending on other tasks, depending on how much time this task is waiting, some instances can have a lower priority or a higher priority, right. So, these are dynamic priority algorithm. So, let us take one small example here. So, let us look at this task set. You have 3 tasks T1, T2, T3, and you have their periods 4, 6 and 8, let us say in milliseconds, and executions time 1, 2 and 3. So, if you calculate their execution time, given these periods and utilization time, let us do their utilization check. That suppose I am trying to first see, well, are these tasks together RM schedulable? Can I execute the RM algorithm on these tasks, on these periodically repeating tasks, and still get a valid schedule? But you already have that utilization constant, right. So, you know that with RM, if I have a 3 task system, my maximum utilization that the RM algorithm will provide me is this. So, what is this? If you remember that formula for RM for computing this upper bound on the maximum utilization that an RM algorithm can give. So, just put n equal to 3, it gives you this 0.7798 something like that. So, that is the maximum utilization you can have for a task set of 3 periodic tasks that RM can give you, right. But in this case, if I have to satisfy this task set with these execution times, the utilization I really require is something like this. So, you see 1 by 4 plus 2 by 6 plus 3 by 8, it goes to something like this, right. So, this is 6, 8 and 9, yeah. So, that is it, right. So, this is the requirement of utilization for executing this task set. and the maximum utilization for a set of 3 tasks that RM can support is this, right. So, the requirement is much more than what can be supported by RM, right. So, this might not be as per the math here, it is not RM schedulable. So, let us see that it is actually so. I mean, let us try to create an RM schedule here. So, I am just trying to roughly draw a timeline here. So, if I follow rate monotonicity, T1 has the highest period, right, followed by T2 and then T3. So, there is no offset here, that means all the instances, the first instances of all the tasks, we can assume that they have all arrived at the right at the point t equal to 0. So, T1 being the task with highest priority will execute here, T1's first instance, right, and then T2 will execute, right, T2 will take 2 cycles. So, T2's first instance, then T3 which has an execution requirement of 3 cycles will start to execute, but you see I mean T3 is going to take 3 cycles, that means T3 is going to finish here, and then T1's first instance is done, but T1's second instance is due to arrive here, right, at this point. At this point T1's second instance comes, and being of the highest priority, this is T3's first instance, and here you will have T1's second instance coming and getting executed. So, once that is done, T3's first instance can resume. So, it will resume, but then again T2's second instance will arrive at this point, and that has a higher priority than T3, right. So, here T3 is in this case here T2's second instance will start, and it will take 2 cycles to execute, and it will end here, right. Now, so if you see T3's first instance which was supposed to take 3 cycles, has it completed? Not really, because here it consumed 1 cycle, here it consumed the second cycle. So, here T3's first instance, if it gets 1 cycle free CPU, it can execute, but the issue is this is its deadline, right. This is T3's deadline. By this point we are considering period equal to deadline here, and at this point T3's second instance has also arrived, right. At this point T3's second instance has also arrived, and T3's first instance was supposed to be executed inside its period equal to deadline equal to 8 millisecond. So, that is what that's just to show, I mean with the example that RM will not really work here, tasks will start missing their deadlines. So, now we can just check, is EDF going to work? Let us try to construct this schedule again, but now with respect to EDF. So, you have T1's first instance starting and completing right there, and now let us see, I mean what is EDF doing. So, at any point whenever a task arrives, it will see which one has the earliest deadline and it will just execute it, right. So, all the first instances have arrived at t equal to 0 and T1 has the earliest deadline. So, that is now executed, right. So, when is T1's next instance going to come? So, here T1's second instance is going to come, here T1's third instance is going to come, T2's second instance is going to come here, this is where T2's first instance has come, this is where T2's third instance will come, T3's first instance is also coming here and T3's second instance is also coming at 8, okay, and that is how it is. So, if you see here T1's first instance is done and T2's first instance is pending, T3's first instance is also pending and T3 has a earlier deadline with respect to T3. So, T2 can execute for 2 cycles and it will get done here, and then now comes the thing, T3 first instance will now start, because right now nothing is pending, right. So, T3's first instance starts, but then T1's second instance comes right here. Earlier in RM, T1's second instance was preempting T3's first instance. Will that happen now? Actually no, because you see T3's first instance that has a deadline up to when? Of course, up to T3's second instance, which is right here, right. It is right here, and T1's second instance has come, T1's third instance, well, that also has a deadline which is right here, right. So, it is like a tie, I mean none of them, I mean I cannot say here that T1 has a higher priority. So, in that case I will just choose that, well, whatever was executing, let it just execute. So, I will just let it consume this time scale and T3's first instance will just end. So, as you can see T3's second instance, I will just repeat, is going to come here at 8 and T1's. So, that is the deadline, right, of this T3's current instance, the deadline is this, and T1's second instance which came in between, for it also the deadline is this. So, I am not preempting at all. So, this is a key difference here with respect to EDF. So, nobody misses their deadline and T3's first instance gets executed. Now, after this well, T1's second instance was pending and T2's second instance has also come at this point, but T2's third instance that is quite late here, but T1 second instance is the earlier deadline. So, definitely T1 second instance will get executed, and after that T2's second instance can just start. Because right now nothing was pending. Now, at this point while T2's second instance was executing, something at higher priority and something at lower priority both came with respect to RM, but they are not really having a higher priority, because for both of them the deadline is much later. The actual deadlines, T1's third instance is this, T1's fourth instance the deadline is here, and T3's second instance has come here, and that deadline is also far away, right. So, nobody will preempt and T2's second instance will also complete, right. And then after this, well, you will execute T1's third instance, and then you will execute T3 is the second instance. And in this way this task set will, I mean if you draw is further, I mean I do not think there is any point in for me to continue this. So, if you just keep on drawing this further, you can see that well for this task set at least things are nice and schedulable, and you can just schedule this task set with EDF. Now, the question is well how do I know that a given task set is I mean schedulable with EDF? Well, for EDF you can actually achieve a utilization which is up to 1, unlike RM for which the achievable utilization is bounded like this. With EDF the upper bound is 1. So, if we just want to summarize this, it is a dynamic priority scheduling algorithm. That means, the priority assignment to task instances is dynamic. Say for the same task different instances can have different priorities. It is optimal with respect to feasibility among all dynamic priority schedulers. So, just like for all fixed priority preemptive schedulers, RM was optimal with respect to feasibility, EDF is optimal with respect to feasibility among all these dynamic priority schedulers, of course, the preemptives also. It minimizes the maximum lateness like we showed using that example for the 2 task system. And the good thing about EDF is it results in fewer preemptions. If you remember our previous example, in many cases where RM would have actually a task arrival in would have resulted in a preemption because of the fixed priority thing, but we actually saw that well although a task arrived, but for the existing task which is executing due to its pending deadline it had higher priorities, right, and that is why there was no preemption. So, that is why we are saying that typically EDF will result in fewer preemptions, which is also efficient, because more for a practical implementation preemptions lead to a context switch overhead because the processor has to restore the state of some system, some task, store the state of some executing task, etc. So, all that time is not lost. And an EDF schedule which has less than 100% utilization, it can tolerate increase in execution time or reduction in periods and still remain feasible, because it has some slack, right. So, suddenly due to some uncertainty the execution time increases or a period reduces, it can tolerate it better because it can go up to 100%, and if it is less than 100% it has got that slack available, right. However, if you see all the algorithms we have discussed till now, none of them have taken precedence relation among tasks into action into consideration, and what we will do in the next lecture is we will now bring in these precedence constraints and see that well with such precedence relations how task scheduling can be done in a real time system. Thank you.